Hi, my name is Devon Yeblonski. I'm here from Mercury Systems as a product manager in our sensor processing group. We've traditionally made high processing, highly ruggedized, secure embedded processing systems for applications such as radar, signal processing, electro-optical, electronic warfare, and now working on new applications such as artificial intelligence. Last year I was here, I talked about the emerging trends we were seeing in artificial intelligence. And I wanted to follow that up and talk to you about what we've seen now since then, since we introduced that concept, and see how that's emerging in the market. So I'm going to start with a story about Cher and me. I think now as I'm getting a little older, I'm actually starting to get interested in history, where I always hated that as a kid. So learning World War I think I was supposed to learn that in high school. So World War I, 1918, it's October. We're in the Argonne Forest where Americans are going up against the Germans. There's about 550 men in this battle. They separate into three flanks. There's a left, right, and a center flank, and they're encroaching in on the battle territory. And what happens is the center flank gets out ahead of the left and right, unknowing to the different sides. So what happens is they get surrounded by the Germans because they're out ahead and there's no protection for them. And they're caught on a hillside. They're really kind of screwed, right? So they got, on top of it, the Americans are bombing where they think the Germans are, which is actually where they are. The Lost Battalion is sitting there. So there's over 30 friendly fire deaths, and they were pretty much at their last wits. At the time, all you had was very short-range radio communication. You didn't have cell phones, satellites, things like that. What you had is messenger pigeons. So you tie the note around the pigeon, goes flying back and delivers the message. Very high speed, high throughput network. So what happens is they have these pigeons, they start sending them off. But remember I said they're surrounded by the Germans, right? So the Germans are there, they know the deal, they shoot down the pigeons, no communication. They have one pigeon left, Cher l'ami, I think is how you pronounce it in French, I'm not good at that, sorry. But they send the bird up, last hope, 30 feet away, it gets knocked out of the sky, shot in the chest, falls to the ground. So it seems like time's up. There's 194 people still out there, and that was their last hope. But kind of like a movie, the bird gets back up, starts taking off, flies through the battle, flies 25 miles through the direction it got shot at, over the Germans, gets back. The Americans pick up the note. It says, "For heaven's sake, stop." And with that message, 194 people were able to they cleared away so they could retreat and save their lives. So the message there is that in battle, networks are always going to be unreliable. They're the number one target. They always will be, no matter how good and fast our networks will be. We need to prepare for that. So performance at what we call the tactical edge, when you think of cloud, fog, and edge, all the way out at the edge assets is the most paramount thing. So today's battlefield looks something like this, right? So many assets. We got small, large, autonomous. We have the cloud sense. We have data centers, like government data centers, or those built around the world to support collaborating all the data together. We got base stations. We got the edge assets. We got all kinds of networks. We got satellites, cell phones. We got all this stuff going on. The problem is big data, right? So we got all these environments for processing the data. The sensors are getting more and more capable in capturing higher and higher resolution data. We want to get information out of that to be able to help us. But there's also the temporal latency problem, right? So we got all this data. What do we do with it? We either process it at the edge, or we aggregate it, and we bring it back to these centralized locations. But the threats today are even more high performance. They're getting more complex. You think of hypersonics. Hypersonics are super fast weaponry that even a human trying to detect them and deciding what to do may not be quick enough. So we need computers to help us. We need those computers to be far out where we're seeing these devices enter the battlefield and be able to detect them. And when you think about it, it's also an interesting problem, right? Is that typically we would capture all this data from the sensors, we'd bring it back to the depot, we'd unload it. Every bit you need to store on the platform to bring back to your depot is a pound or an ounce that you can't use for computing on the data. So the big data problem becomes even more important. So artificial intelligence, I talked about it last year. It's really a tool for processing big data. So that's why it's so important to our industry. It's how we're going to detect those hypersonics. I mean, there's been things in the news with airliners and things like that. Classifying data is important. We need these applications to help us with that big data problem. It is redefining global power. It's going to be how the future military forces compete to see who has superiority in the skies, on the ground, and in the sea. And what we've seen over the past year as far as trends from this market is that the government has invested a lot into our industry to try to help us bring capability from the commercial environment back out to the defense industry. And that's where we play a big part in and help transition those technologies from commercial to defense. So that's going to be really important, and we're seeing more and more investment. We've seen more and more opportunities where people are actually trying to build this capability into the platform. We're seeing it a lot in terms of converged systems. So where do you have the data? Where is that big data residing? That's the best place to do it, because as soon as you have to drop data to either use a slow data link, to be able to bring it back to your depot, that's when you end up with problems. So the problem is that this is what the artificial intelligence environment looks like in commercial industry that we're trying to bring to defense. And this is Amazon servers around the world. You got super high performance Charlemies flying your data all around to these data centers. If you take your Amazon Alexa and you unplug the internet cable, or you turn off your Wi-Fi, I guess, and you say, what time is it? It can't answer. Your phone can't answer you without the internet. It knows the time, but it can't figure out what you said to it because it's using these data centers around the world. In these data centers are big iron data center class processors. That's where the applications are being developed. That's where all the Googles, the Amazons, the Facebooks that are making these great algorithms that we want to bring into defense. That's where they're residing. That's the architectures they're built for. So all of that fails to translate to that tactical edge, to those edge assets where we need to do the processing. So what does the tactical edge look like? If we want to build a computer that can do this artificial intelligence at the edge, what are the challenges? So the first one is lack of external networks, lack of access to the cloud. That's what I talked about how we can't depend on the networks being there. We don't want to leave the lost battalion out there just stranded when the network goes down. We have to plan on it being down. So that means more compute at the edge. Harsh environments. The harsh environments are temperature, altitude shock, something that those commercial processors are not built for. The processors people are asking us at Mercury for don't come in soldered down, chipped down designs. They're not, the networks they employ can't handle the signal integrity across temperature, all aspects like that. Limited power, so we talk about watts and kilowatt, sub-watt levels for power, where in the data center you're usually trying to optimize hopefully for hundreds of watts or megawatts. So the granularity of what we're interested in low power and power efficiency is really important. Space and weight limitations. Now that we're building higher and higher capability processors and modules, we're not seeing people say, great, you saved 20 pounds off the system, we're going to give you a credit for that. They're saying, all right, what do we do with the last 20 pounds? How do we add more modules in there? How do we add more capability? They'd rather give up on paint on the box than they would on a bit of compute power. Life cycle, 10 years or more, that's one of our biggest challenges of trying to bring these data center capabilities into the defense market, which is how do you support some of these processors for 10, 15, 20 years when the industry moves past them very quickly. It's very expensive to develop a computer that can perform in these environments, so we want it to last a long time. We want it to be upgradable. For instance, one of the trends in the market is that Moore's law is no longer a thing. Artificial intelligence is doubling in the pace of 3 to 6 months. And what that's doing is it's generating a lot of new types of processors. There's a lot of greatest hit, new ASICs coming off the press, and 3 to 6 months later, there's a new one. That doesn't work at all for our environment, unless we're willing to, say, stock those devices for 15 or 20 years, and we're looking into those kinds of solutions. But what we're seeing more of is what is the best performing long-term processor that we can supply. And even there's some of those challenges of what is an embedded Xeon processor versus a scalable Intel processor. They really want the scalable ones. The Xeon D processors have the long-term lifespan, and that's the gap we try to bridge. We try to help customers both work with the vendors to supply the parts that they want for longer, as well as to deliver the processor in a more reliable, long-lasting form, and also doing our own work for extended life cycle on these processors. And mission critical safety and security is another aspect that's really important. So the Amazon data center is not too worried about safety certifying any of the architecture they're using or relying on those processors. They're not worried about the data center falling out of the sky in someone's head or misclassifying a missile or a jetliner, right? Security, Amazon's data centers aren't flying into enemy battle and getting worried that they're going to get picked up and then be tampered with, right? So that's another challenge of the tactical edge. So we want to try to take, and the government's investing in us trying to bring artificial intelligence capability into the defense market. All these challenges are what we have on our plate to deal with. So we have this concept of the common composable data center. What that means is that at that cloud, fog, and edge environment, we want to deliver that same architecture. So again, it's the high performance networks, the high 100 gigabit Ethernets, the Xeon class scalable processors, the NVIDIA chips that are running out in the data center performing artificial intelligence. We want to develop that same architecture, be able to deliver it in the fog. So the fog is basically take your rack mount server, compress some of the density out so you can fit more in a smaller package, so you can be on a large ship or a large plane, things like that. Maybe you bracket down your memories, you add some physical ruggedization to it. Or the tactical edge, where my group works a lot, which is the VPX environment that most of you here know pretty well. And that's where Mercury's worked for a long time. And that's where we're developing the artificial intelligence capability, processing that goes in these small assets, the unmanned aircraft, the fighters, high impact ground stations, ships, et cetera. So the anatomy of this kind of environment starts at the module, right? So at the module level, as I mentioned, it's incredibly expensive, costly to build, to those tactical edge requirements. So what we do is we build a generic PCB that has all the capability in it, but can support 7 to 8 or 9 different cooling solutions. So that includes conduction cooled, airflow by. Something that we're seeing a trend a lot, especially in the artificial intelligence space, is liquid cooling. That's been a big one in our industry the last several years, but is really ramping up now that we're being asked to work in this kind of application. That's because they're looking to push 200, 300, even more watts per slot in some cases. So you can imagine how challenging that is. Sometimes we even do hybrids of liquid and air cooling. We have to build these with the capability to ramp up features in terms of off-the-shelf, modified off-the-shelf, military off-the-shelf kind of capability, such as increased conformal coating. How do you handle 80,000 feet instead of 50,000 feet, or the next generation of, the next level of security protection? On the board itself, Mercury is working on stacking chips three-dimensionally to be able to use up that inch of space, because if you don't need it for metal, that's something you can use for processing, right? And that's how we can squeeze more into there. So we're doing three-dimensional memories, system unpackaged chips, squeezing components down into tighter and tighter spaces. The connector industry we're working with very closely to once again push the boundaries. We were talking about the optics a little bit earlier. We're looking to be able to do the 100 gig networking on copper across these backplanes, as well as through Vita66 and things like fiber optics. So we're working with the connector industries to help lift all the boats and get to that where we can all work together at those speeds. Open architectures are incredibly important. They continue to be. Mercury had a big part in developing the VPX environment. We're working this week, I think we're at a Plug Fest this week doing with SOSA, continuing to go to the next generation of open architectures. That's all around the needs of, especially in these artificial intelligence environments. How do we handle upgradability in the future? How do we handle the end of life concerns? And then take that to a system aspect. We take it to the next level and we do the backplanes to incorporate some of the technologies you've already seen today, the military connectors, the fans, the cooling solution, the software interconnect, the fabrics, bring that all together into a complete subsystem, or an artificial intelligence subsystem, if you will. Just some examples of the modules we're developing that apply to this market that I'm working in the artificial intelligence space. High density servers. So what happened actually with the Xeon D Intel processors recently is that they haven't had really a performance boost in the past couple of years, and we don't see something coming up in the near future. So the fact that we're doing the scalable processors from Intel got us to Cascade Lake, which even improved on performance of the previous generation Skylake and the Sandy Bridge processors, with increased vector engines and things of that like. So that's been incredibly important to this market that's looking for more processing. PCI Express switching. So We're working with the standard industries, hopefully to adopt this, because what we're seeing is that, especially in the artificial intelligence market, it's all about accelerators. It's GPUs, it's FPGAs, it's these new ASICs, and their fundamental, bus is PCIe. Usually you have to convert that to go across systems over to Ethernet. But in this environment of VPX, we don't have the challenges that the data center has of cables and hot swapping and new people entering the network all the time. We have that fixed backplane that everything's connected together. It's essentially one motherboard when you think about it. So the most cost-effective way to do that is with PCI Express switching between your devices. It saves you latency, it saves you cost from having endpoint NICs. So we're developing modules to support that environment. And then I/O. The more I/O you can squeeze into the box, I told you about the sensors that are continuing to improve in performance and capability. I/O is pretty much always a desire. How much more can we fit in that small area? So from our composable data center point of view and for an artificial intelligence system, this is the kind of systems that we're being asked to build in the past year. The AI processor, the APE that I introduced last year, we're in our second generation of it. So it includes, say, that Intel processor, the scalable processor at the top. Usually that's used to do a lot of control processing for all the accelerators, to process your data and format it in a way that artificial intelligence and machine learning can handle it. Then you have the PCI Express infrastructure, so saving a ton of cost over needing to rely on the Ethernet and InfiniBand network endpoints and those switches. Being able to switch the PCIe fabric and attach a lot of accelerators to one CPU processor is important. Without those switches, you usually can only do a couple GPUs per Intel host. And then those PCI switches can squeeze onto their mezzanine cards for tons of I/O that directly pipes into that PCIe fabric. Again, the native fabric of the accelerators, right? So we can bring data with zero copy in from your fiber optics on the outside, pipe it into an accelerator's memory like a GPU, and process it immediately. So that, for things like hypersonics and these new high-speed challenges that we're dealing with, that's incredibly important. And then we're working on a lot of accelerators like the NVIDIA GPUs, like Xilinx FPGAs, et cetera. And all of this fits into about 9 slots, 9 inches wide. And this, the reason why people are finding this really interesting is it mimics, what's out there in the Googles and the Facebook's data center. It's what you can go to NVIDIA's catalog and buy off the shelf. You can buy that architecture in a data center platform, and we can do that in the composable edge data center. So last year I had a scary robot up here talking about AI and what the future would bring and how we're scared of it. Maybe this is even more scary as artificial intelligence, improved pigeons. Really hoping I can create a product someday called Pigeon, and it's a networking project. It'll be great and follow up to this. But we don't know what's coming from this artificial intelligence. We know it'll be there. I know it'll be there. We're currently developing systems like this for the future platforms. And these are the challenges we're working today, bringing this capability to the tactical edge. With that, I'll take questions.